The ultimate objective of practical statistics is inference. We observe a small subset of individuals to make mathematical generalizations about a massive, unknowable population. To execute this, we must extract a random, representative sample, ensuring all elements have an equal chance of selection. This table shows a raw grid of 34 sample data points. In this state, the data is chaotic and unstructured. It is impossible to interpret simply by looking at it. Applying predictive mathematics directly to this grid treats every number with equal weight, failing to distinguish between a category code and a physical measurement. Before any predictive modeling can occur, the dataset must undergo strict architectural classification and exploratory data analysis to reveal its true mathematical shape. We start by isolating a single variable, an observable characteristic that can be measured across individual units in a sample. This diagram shows the primary split in data classification. Variables must be sorted into quantitative numerical data or qualitative categorical data. The quantitative side breaks down into continuous measurements or discrete whole number counts. The qualitative side divides into nominal categories or ordinal rankings. This list of examples demonstrates the rules for measurement scales. Air temperature in Celsius is a continuous quantitative interval scale. The 0 point here is arbitrary. It does not represent an absolute absence of temperature. Conversely, monthly income in euros is a quantitative ratio scale. Here, differences and ratios are meaningful because 0 represents a true physical absence of money. Qualitative data follows different logic. The type of employment contract is a qualitative nominal variable. The categories exist, but they possess no mathematical rank. Identifying exactly where a variable sits on this taxonomy flowchart is the non-negotiable first step that dictates every statistical operation allowed moving forward. Returning to our 34 individuals, we can apply this taxonomy. The first column records exact numerical monthly income, operating strictly as a quantitative ratio variable. The second column groups that income into 4 ranked tiers, transforming the data into a qualitative ordinal variable. The exact same real-world phenomenon is now coded as 2 distinct mathematical objects, each requiring completely different analytical tools. This slide outlines exploratory data analysis, or EDA. It functions as a mandatory diagnostic checklist required before computing basic statistics. The mathematics demand that observations are mutually independent and originate from a population with a normal distribution. We must assess the degree of skewness and kurtosis, specifically searching for extreme outlying values that could corrupt the math. Blindly computing averages without first clearing this EDA checklist produces mathematically invalid models. Variable type severely restricts descriptive choices. Qualitative variables cannot use averages at all, locking nominal data to the mode and ordinal data to the median. For quantitative data, the arithmetic mean serves as the primary measure of central tendency. It operates under a strict physical constraint. The mean is the exact point in a distribution where the sum of all deviations equals 0. If a massive extreme outlier enters the dataset, the balance breaks. To maintain its zero-sum equation, the mean must shift toward the outlier. In a right-skewed distribution, this movement pulls the average away from the center of the data's density, distorting the calculation. Compare this fragile balance with the median, a robust, position-based metric. The median determines the center strictly by rank order. Because it only finds the value dividing the upper and lower halves of frequencies, it ignores the raw numerical size of outliers at the edges. Selecting between the mean and the median is a strict defensive requirement, dictated by the skewness and outliers found during exploratory data analysis. This flowchart visualizes the complete statistical life cycle. It begins here with the messy reality of data collection. Moving to the center, data analysis applies variable taxonomy and EDA to structure the raw input. Only an accurately classified dataset can safely pass into the final phase. Statistical inference generalizes these clean sample conclusions back to the entire population using probability. A classification error or an ignored outlier creates a flaw in the descriptive foundation that compromises every subsequent probability calculation during inference. Descriptive statistics and exploratory data analysis act as critical gatekeepers,
isolating mathematical truth from analytical illusion.